Welcome to my presentation. My presentation topic is Statistical Multipath Channel Models. Here, as I have given a scenario, we can see that a object is moving and it gets reflection from different scatterers. The signal can be received from the transmitter through direct path or through reflected paths. Here are the contents on which my presentation gives an outline. The introduction for the multipath channel models, types of multipath model, which includes time varying channel response, narrow band fading model, wide band fading model, discrete time model, space time model, and finally comes the conclusion. Fading. It is an important parameter. Fading is caused due to multipath. It indicates the rapid fluctuation of received signal strength over short time intervals or travel distances. Let us consider a scenario where we are considering a base station and a mobile station. A base station is transmitting signal to mobile station. If the receiver is mobile in the environment, then the transmitted signal will be received at the receiver by reflecting from the multiple scatterers. The received signal may consist of some delays which can give the receiver a multiple copies of transmitted signal. The multiple copies of transmitted signal arriving at the receiver at slightly different times can cause interference. Fading. There are three more important effects of fading. First, rapid changes in signal strength over travel distances. As I have considered a mobile station, in a mobile environment, the receiver is moving and rapidly changing its position. As the receiver is changing its position, the signal which is being received by the receiver is reflected from the scatterers and then received, which leads to the loss of signal strength. Another effect is change in frequency of signal. As the receiver is moving from its position, frequently the received signal also changes the frequency accordingly. The another parameter is multiple signals arriving at different times. As I have considered that the mobile station is moving from its position, the signal which is being received by the receiver consists of some delay as it is receiving at different time intervals. When they are added together at the antenna, signals are spread out in time. Here are the type of multipath models. First is time varying channel impulse response. Let us see the transmitted signal to be S of t, where S of t is the real part of u of t e to the power j 2 pi fct, where u of t is the complex envelope of S of t with bandwidth bu and fc is its carrier frequency. U of t has two components, cos 2 pi fct, sin 2 pi fct. It means it has different phases. The received signal at the receiver is the sum of line of sight path and all resolvable multipath components, where the received signal is r of t, where the summation of n is equals to 0 corresponds to LOS path. N of t is the number of resolvable multipath components. A of n is equals to the amplitude. U of t is the complex envelope of S of t, where the tau n of t is the corresponding delay. Phi dn is the Doppler's phase shift. Here is the scenario for multipath propagation that leads to fading. Here I have considered a scenario which I have also mentioned earlier, that the object can receive signal directly in the line of sight path, and it can receive signal from the reflected path, which is being reflected by different scatterers, such as the components present in the surrounding, which can reflect the signal. Here, the antenna, where it transmits signal A and signal B. Signal A plus signal B is the total signal sent by the sender. If they are in phase, A and B are in phase, then Y is equals to A plus B. If they are out of phase by pi, then Y is equals to 0. Means if they are not in contact, the received signal is 0. Means no direct path, no non-line of sight path. Here, for every stationary transmitted or received wireless link can experience fading due to motion of objects such as car, people, trees, buildings, etc. in the surrounding environment, which comes to the reflection. There are certain objects present in the environment due to which multipath is created. Multipath is equals to several delayed replicas of the signal arriving at the receiver. Multipath is the signals which are received at the receiver at different time delays. Some factors are influencing multipath propagation. First one is multipath propagation. Multiple versions of signal arrives at the receiver. This can cause signal disturbance due to symbol interference. Another, speed of the mobile. It results in random frequency modulation due to Doppler shift of each multipath components. Next, it is the speed of the surrounding object. If the speed of the surrounding objects move at a greater rate than the mobile, then it affects or dominates the small scale fading. Another is transmission bandwidth of the signal. If the transmitted radio signal bandwidth is greater than the bandwidth of the multipath signal, the received signal will be distorted, but the signal strength will not fade over a local area. Here is the classification on the basis of fading. It is divided into two categories. First, due to static multipath, delay spread occurs. On the basis of delay spread, flat fading or frequency selective fading is decided. Another fading is due to dynamic multipath, Doppler spread is caused. And due to Doppler spread, we can decide fast fading or slow fading. Delay spread. It is the time dispersive nature of the channel. Delay spread is caused due to the received signal. As the signal is received at the receiver at different time delays causes the delay spread. The delay spread is equals to the time delay between the arrival of first received signal component and the last received signal component related with the single transmitted pulse. Delay spread helps us to calculate another parameter, that is coherence bandwidth. Coherence bandwidth has a relation with the delay spread, as coherence bandwidth is inversely proportional to the delay spread. If delay spread is small compared to the signal bandwidth, then there is a little time spreading in the received signal. If the delay spread is large compared to the signal bandwidth, then there is a time spreading of received signal, which can lead to signal distortion. Channel delay spread is highly dependent on the propagation environment. In indoor channels, delay spread typically ranges from 10 to 1000 nanoseconds. In suburbans, it ranges from 200 to 2000 nanoseconds, and in urban areas, it ranges from 1 to 30 microseconds. Doppler spread. It is the dispersive nature and frequency domain. Doppler spread is caused due to the high speed motion of the receiver. As the receiver is moving from one place to another, the frequency also changes accordingly. So the variation in frequency due to the motion of the receiver is Doppler's frequency, and the delay caused due to the Doppler frequency is Doppler spread. Time varying fading due to the motion of the scatterer or the motion of the transmitter or receiver or both is Doppler spread. Doppler spread is helping us to calculate another channel parameter, that is coherence time. Coherence time defines that the time duration for which channel is considered to remain constant and offers approximately equal gain. Coherence time is inversely proportional to the Doppler spread. It is caused by time selective fading. That is, for a particular instant of time, channel behaves as a fading channel, and for the rest, it behaves as a flat channel. On the basis of Doppler spread, there are two types of fading: fast fading and slow fading. Fast fading is occurred when the channel response changes rapidly with symbol duration. Slow fading occurs when the channel response changes at a much slower time than the transmitted symbol bandwidth. So the fast fading is having signal bandwidth is less than the Doppler's bandwidth. In slow fading, the signal bandwidth is greater than the Doppler's bandwidth. Apart from the time varying channel response, there are another types of fading model, that is narrow band fading model and wide band fading model. Narrow band fading model, in which delay spread of a channel is small to the inverse signal of bandwidth of the transmitted signal, as it has been expressed below. In the wideband fading model, multipath delay spread is less than the multipath components that are received. If the multipath delay spread is greater than the time, then each different multipath components can be resolved. Narrowband fading model is just defined as flat fading, and wideband fading model is just defined as frequency selective fading. In narrowband fading models, there are certain parameters such as level crossing rate. As it is shown in the figure, it defines that how often the signal goes for deep fade after crossing the threshold level in a positive direction. The number of times it goes in the deep fade condition, the signal is lost, and it can be difficult to recover the lost information in the communication channel. In the figure, A is the amplitude of the signal. Amplitude defines the threshold level beyond which the signal deteriorates, indicates deep fade condition. For the deep fading, the speed can be related with the amplitude, at which speed the receiver is moving from one place to another can lead to deep fade condition certainly. The fluctuating signal crosses the amplitude again and again, that is known as threshold. As here it is formulated, LCR is equals to n by t, where n is the number of times it goes beyond the threshold level and t is the time duration for which it goes for the deep fade condition. Here is the classification on the basis of fading. It is divided into two categories. First, due to static multipath, delay spread occurs. On the basis of delay spread, flat fading or frequency selective fading is decided. Another fading is due to dynamic multipath, Doppler spread is caused. And due to Doppler spread, we can decide fast fading or slow fading. Finite state Markov channel. It is a channel which is suitable for narrowband fading models. The complex mathematical characterization of flat fading can be difficult to incorporate into wireless performance analysis such as packet error probability. Finite state Markov channel, it is such a model that captures main features of flat fading channels which is needed for analytical calculation. It is approximated as discrete Markov process with time discretized at an interval t. The set of all fading channels is modeled as set of finite channel state. Channel varies over these states at each time interval t according to a set of Markov transition possibilities. Finite state Markov channels are used to approximate both mathematical and experimental feeding models including satellite channels, indoor channels, relay feeding channels, Rayson feeding channels, and Nakagami M feeding channels. It is also used for system design and system performance analysis. Finite state Markov channels are used for fading modeling for amplitude variations only. Coherence bandwidth is another parameter in the wideband fading models. Coherence bandwidth is used to characterize the channel in frequency domain. Coherence bandwidth indicates the range of frequency over which channel is considered to remain static and offers approximately equal gain and linear phase response. Larger coherence bandwidth of channel indicates wider range of frequencies for which channel response remains unchanged. It is a statistical measure of range of frequencies over which channel can be considered flat. If correlation is above 0.9 means 90%, then the coherence bandwidth is 1 by 50 sigma. Sigma is the delay spread. If the correlation is above 0.5, that is 50%, then coherence bandwidth is 1 by 5 sigma. Sigma is the delay spread. Another statistical multipath channel model is discrete time model. Discrete time approximation for the wideband model can be used. It is used on the basis of physical propagation environment consisting of composition of isolated point scatterers. Here we can see that a satellite is being received the signal from the object which is reflected by the different point scatterers. Discrete time model is useful in spread spectrum systems. The discrete time approximation for wideband multipath models can be used. In this model, the multipath components are assumed to form subpath clusters. This discrete time model can be denoting the signal bandwidth coming from the different subpath clusters. Another model is space-time channel model. Nowadays, multiple antennas at the transmitter or receiver are very common in wireless system due to their diversity and capacity benefit. A typical model assumes that the channel is composed of several scattering centers which generate multiple paths. Systems with multiple antenna require channel model to characterize the angle of arrival and characteristics of the channel, the location of the scattering centers relative to the receiver responds to the angle of arrival of the corresponding multipath components. These models can be either two-dimensional or three-dimensional, which is the main benefit for the multipath channel models. Here is the conclusion for the statistical multipath channel models. To design these models, we need to have a deep understanding of multipath characteristics, knowledge on the antennas, knowledge for the basics, and knowledge for the channel parameters. There are certain characteristics which are to be emphasized for the communication system design. These models are mostly applicable in urban environment, as in urban environment there are more scatterers in the environment, due to which we can get multipath components at the receiver side. The data of the multipath characteristics are mainly obtained by the real-time navigation. We cannot get the assumed navigation for the perfect construction of the statistical channel models. Thank you everyone for watching this presentation.